Hey guys, Spiderivative Man back to tell you about differentiability and continuity. Another question, what's Spider-Man's favorite kind of rice? Uncle Ben's.
First thing we're going to do is review the derivative of a function at x. That's the instantaneous rate of change or amount by which a function changes at a given x value. The derivative of a function is equal to the slope of the tangent line at the given x value. So if you recall, last time we talked about some things that all meant the same thing. The derivative of a function at x is the same as the instantaneous rate of change at a given x value, which is the same thing as the slope of the tangent line at a given x value, which is the same thing as the slope of your function at a given x value. All of those things mean the same thing. Here, we're taking the derivative, and when we take the derivative this way, we're getting a function out. And that function will allow you to find the slope of your original function at any given x value. Down here, you are finding the specific slope of your function at a given x value, c. That's why you see we're plugging in c here for these particular derivatives. These derivatives give you a slope, a number, at a particular x value. These give you a function that will allow you to find the slope of your original function at any given x value. The next vocabulary term is a differentiable function. That's a function whose derivative exists at each point in its domain. So down here, all this is referring to is that can you draw a tangent line to the graph at every point in the function's domain? So in this graph right here, we can draw a tangent line to the curve at any given x value that you choose in its domain. Same thing here. We can draw a tangent line to the curve. Well, this isn't really a curve, it's a line, but if I were to draw a tangent line to a line, it's just the same line. So both of these are differentiable. Over here, we have two functions that are not differentiable at x is equal to 0. So you can see right here, at x is equal to 0, we have a corner. Now you may think you could draw a tangent line to a corner that's straight across, but you can't because there's no accurate way to draw a tangent line. There's no way to get a slope of this corner. Therefore, the function is not differentiable at x is equal to 0. Same thing here. We have an asymptote, and there's no way to draw a tangent line to the function at an asymptote. So you say both of these functions are not differentiable at x is equal to 0. Now let's quickly review the alternative form of the derivative. It's just f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. Again, this gives you the slope of a given function at a particular point. It's the derivative of the function at a particular point. It's the instantaneous rate of change of your function at a particular point. So when you use this form of the derivative, you're going to get a number out, and that number is the slope of your function at that given point. Now let's quickly review the definition of tangent line with slope m. So all this is saying is that if you were to evaluate this limit, the alternative form of the derivative, the limit as x approaches c of f of x minus f of c all over x minus c, it will give you the slope of the tangent line to the graph at point c comma f of c. We also want to note again that the slope of the tangent line to the graph of f at point c comma f of c is the slope of the function at x is equal to c. It's the derivative of the function at x is equal to c. It's the instantaneous rate of change of the function at x is equal to c. Remember that. Now theorem 2.1, differentiability implies continuity. This says if f is differentiable at x is equal to c, then f is continuous at x is equal to c. So what this is saying is that if you look at any function and at x is equal to c, you can draw a tangent line to the curve and get the slope of that tangent line. Or you can calculate the slope of the function at that particular x value, c. Then you know the function must be continuous also at that x value, x is equal to c. Over here, we see that at x is equal to 0, this has a vertical asymptote. Therefore, the function is not differentiable at x is equal to 0. Therefore, we cannot say that the function is continuous at x is equal to 0. Here, on the other hand, we want to look at our note. It says if f is continuous at x is equal to c, it is not necessarily differentiable at x is equal to c. So if we're looking at this function, we see that it's actually continuous at x is equal to 0. However, it is not differentiable at x is equal to 0. And that's the reason we have to note that just because a function is continuous doesn't necessarily make it differentiable. But if it's differentiable, if you can find the slope of the function at that particular x value, then you know the function must be continuous at that particular x value. Now, we're going to go through a couple cases of when a function is not differentiable. So the first case would be a vertical tangent line. If f is continuous at x is equal to c, and the limit as x approaches c from the left of f of x minus f of c all over x minus c equals the limit as x approaches c from the right of f of x minus f of c all over x minus c, and they both equal infinity, or coming from the left and coming from the right, they both equal negative infinity, then the vertical line x equals c passing through c comma f of c is a vertical tangent line to the graph of f. So what this is saying is if we have a function and as we approach our c value, in this case it's x is equal to 3, as we approach that value from the left, we see that the slope of our function, the slope of the tangent lines to the function at given x values, as we get closer and closer and closer to 3, those slopes actually end up approaching positive infinity. Same thing if we were to come from the right. If we draw tangent lines to the curve, we see that the slopes of those tangent lines as we approach x is equal to 3 from the right get closer and closer and closer to positive infinity. Because the slopes of the function from either side of x is equal to 3 approach infinity, we know that there must be a vertical tangent line at x is equal to 3. Therefore, the function is not differentiable at x is equal to 3. Note that functions with vertical tangent lines may be continuous, but not differentiable at the vertical tangent. So this function, you can see, is continuous throughout this given interval right here, but at x is equal to 3, even though it's continuous, it's not differentiable because we can't have a derivative of our function be infinity. Therefore, the function has a vertical tangent and it's not differentiable at x is equal to 3. Case 2, where a function would not be differentiable, is that sharp turns. And there's two types of sharp turns we're going to talk about. The first is a cusp, and that's a pointed end where two curves meet. So in this example, you see we have a curve coming in from the left and a curve coming in from the right. Those two curves meet at a point right here at x is equal to 0, and we call that a cusp. This occurs when the slope of your function, the slope of the tangent lines to your function coming in from the left approach positive infinity, and the slopes coming in from the right approach negative infinity, or vice versa. The slopes coming in from the left equal negative infinity, and the slopes coming in from the right equal positive infinity. In this case, this particular function, we see that the slopes of your function, the slopes of the tangent lines to the function, as we approach x is equal to 0 from the right, those slopes get more and more and more negative until at x is equal to 0, we end up getting slopes of negative infinity. Coming in from the right, we see that the slopes of the tangent lines to the curve are actually positive. And as you approach x is equal to 0 from the right, these slopes get more and more and more positive until they approach positive infinity. So this would be our case for our example down here. And you see that the function is continuous, but it's not differentiable at a cusp, because a cusp, it's a sharp turn. There's no way to draw a tangent line to the curve at this particular point. Therefore, the function cannot be differentiable there. Case 2 for a sharp turn is a corner. That's a point where two lines with different slopes meet. So a cusp was a point where two curves meet. In this case, we have two lines meeting. That creates a corner. So in our example down here, you can see we have a line meeting up with another line. Each of those lines have two separate slopes coming in from the left and coming in from the right. Because the slopes equal two different numbers, we say that at x is equal to 5, where those two lines meet up, there's going to be a corner. Therefore, the function is not differentiable at that given x value. So the function is continuous. Corners usually are continuous. However, the function is not differentiable there because there's no good way to draw a tangent line. We have a slope coming in from the left and a slope coming in from the right that are different numbers. That creates a corner. Now, the third case where a function would not be differentiable is at any discontinuity. So a function has the discontinuity at x is equal to c if there's a hole, jump, or an asymptote at that given x value. So we already know about the three different types of discontinuities: holes, jumps, and asymptotes. And now we know that a function with one of those discontinuities cannot be differentiable at that given x value, x is equal to c. So at this hole, the function is not differentiable. At this jump, the function is not differentiable. At this asymptote, the function is not differentiable. And it makes sense because functions that are differentiable have to be continuous, and these functions are not continuous at those given x values. Now let's quickly go over this what to watch for cheat sheet that talks about differentiability of a function. So a function is not going to be differentiable at the three cases that we just talked about: at vertical tangent lines, at sharp turns where we have cusps and corners, or at discontinuities. Now here's what to look for when you're given a function. First, we have a vertical tangent line. Now, a vertical tangent is going to occur when the slope of the function coming in from the left and the right as it approaches some x value c both equal the same infinity. So they either both equal positive infinity or both equal negative infinity. Now, in terms of your function, what you want to watch for is if the function has a variable that is being raised to an exponent that is less than 1, so it's going to be like a fraction, and that fraction has an odd number in the numerator and an odd number in the denominator, then it's going to create a vertical tangent. Let's look at this example over here. We have f of x is equal to x plus 2 the quantity to the 1/3 power. Note that the exponent is less than 1. The numerator has an odd number, and the denominator also has an odd number. Because of that, there's going to be a vertical tangent, and that vertical tangent is going to occur at the x value that causes this in here to equal 0. So what x value causes this in here to equal 0? That would be x is equal to -2. So at x equals -2, there's going to be a vertical tangent for this function. Now, a cusp occurs when the slope from the left side of a function and the slope from the right side equal two different infinities. So if one approaches positive infinity, one approaches negative infinity, then you know you're going to have a cusp at that x value. And now let's talk about what to watch for when we're talking about cusps. So when you see a function, you're going to have a variable being raised to an exponent that is less than 1, just like up here. The only difference is in a cusp, the exponent is going to have an even number in the numerator and an odd number in the denominator. So let's look at our example over here. We have a function f of x is equal to the quantity x plus 2 to the 2/3 power. Note that we have our variable being raised to an exponent that is less than 1. There's an even number in the numerator. There's an odd number in the denominator. Because of that, there's going to be a cusp at whatever x value causes this in here to equal 0. So in this case, it would be x is equal to -2. At x equals -2, there will be a cusp for this function. Now, a corner is going to occur when the slope from the left and the right equal two different numbers. So two main ways that a corner occurs would be in an absolute value function or a piecewise function. So let's first start by looking at this absolute value function. We have f of x is equal to the absolute value of x plus 2. So absolute value functions have a graph that is a V because coming in from the left as x approaches whatever causes this to equal 0, so that would be x is equal to -2. Coming in from the left, we have a slope of -1, but coming in from the right, we have a slope of +1. Because the slopes coming in from the left and the right equal two different numbers, we know we have a corner at x is equal to -2, whatever causes this to equal 0. A piecewise function is also another place where you could have a corner. So if the two parts of the piecewise function meet up at the same y value, but the slope coming in from the left does not equal the slope coming in from the right, you will have a corner at that given x value where they break up. The last thing to look for where a function would not be differentiable would be at any discontinuity, so where the function is not continuous. So that would be at any hole, asymptote, or jump, the function would not be continuous. Again, holes and asymptotes both appear in rational functions. Holes occur when a variable cancels out in the numerator and denominator. Asymptotes occur when the denominator does not cancel out, and it's just at whatever x value causes the denominator to equal 0. A jump occurs usually in a piecewise function, or in this little function right here where you have absolute value of x over x, or absolute value of x plus 1 over x plus 1. These both create jump discontinuities. So this example right here actually has a hole, an asymptote, and a jump. So in this part of the piecewise function, if I were to factor this denominator, it factors into x plus 1 times x plus 4. The x plus 1s cancel out, meaning that there's going to be a hole at x is equal to -1. Because the x plus 1s cancel out, we're just left with 1 over x plus 4. So whatever causes the denominator to equal 0 is going to give you an asymptote. So at x is equal to -4, we're going to have a vertical asymptote. And then a jump occurs at x is equal to 0 where these break up. Because if I plug in 0 up here, I get a y value of 1/4. If I plug in 0 down here, I get a y value of 2. So the two parts of the piecewise function do not meet up at the same y value at x is equal to 0. So there's going to be a jump discontinuity.
Justice League sucks! It's example time!
Now, example 1 says find the x values at which f is differentiable. Confirm with a graphing utility. So here we have f of x is equal to the absolute value of x minus 3. So right away, you see those absolute value bars and you're like, okay, this is probably going to have a corner. So the question is, where is that corner? Well, remember, it's at whatever x value causes this to equal 0 in here. So what x value would that be? That would be at x is equal to 3. So we look at our graph and we see that at x is equal to 3, we have a sharp turn. We have a corner. Therefore, the function is not differentiable at x is equal to 3. Part B, we have f of x equal to 2x over x plus 5. This is a rational function. So right away you're thinking, okay, there could be a discontinuity here, either a whole or an asymptote. So does anything cancel? No. So that leaves us with an asymptote. So there's going to be an asymptote at whatever value of x causes the denominator to equal 0. So that would be at x is equal to negative 5. So at x is equal to negative 5, we should have a vertical asymptote, which we do, meaning that the function is not differentiable at x is equal to negative 5.
Don't be a vulture. Do your own work. You try.
Now, part A, we have f of x is equal to x to the 2/3 power. So we have our variable being raised to an exponent that is less than 1, which automatically makes you think, okay, it's either going to be a vertical tangent line or a cusp. So which one is it? Well, we have an even number over an odd number, and that occurs in a cusp. Now, where does that cusp occur? Well, if you remember our example, it was the quantity x plus 2 being raised to our power, and that meant the cusp occurred at x is equal to negative 2, because that caused that to equal 0. Well, there's nothing else besides x here. So what would cause this to equal 0 would be x is equal to 0. So there's going to be a cusp at x is equal to 0. And you see the graph confirms we have our cusp at x is equal to 0, which means that the function is not differentiable at x is equal to 0. In part B, we have a piecewise function. So first thing we do is we plug in negative 1 here, and we see if the y values match. Here, if I plug in negative 1, I get negative 1 plus 3 times negative 1, so minus 3 is going to be negative 4. And then down here, negative 1 squared is 1, plus 2 times negative 1, that's minus 2, so that's going to be negative 1, plus 1 is 0. So I get negative 4 up here as my y value, and then 0 as my y value here. Therefore, the two parts of the piecewise function do not meet up. They don't have the same y value, which means at x is equal to negative 1, there should be a jump discontinuity. And we see that it does appear to be so. We have a jump discontinuity at x is equal to negative 1. Therefore, the function cannot be differentiable at x is equal to negative 1. Now, example 2 says justify whether or not the function is differentiable at x is equal to 0. So here we have a piecewise function that breaks up at x is equal to 0. We know that the function is going to have a discontinuity if, when you plug in x is equal to 0 for both of these, they don't have the same y value. That means there would be a jump discontinuity. So the first thing we do is plug in 0 for each of these x's. If I do that up here, I get a y value of 1 at x is equal to 0. If I do that down here, I get a y value of 1 at x is equal to 0, which means both parts of the piecewise function meet up at the same y value at x is equal to 0. Therefore, the function is continuous. Now the question is, does the function have the same slope as we approach 0 from the left and from the right? To figure that out, we are going to have to use the alternative form of the derivative. And we're going to use the alternative form of the derivative for both parts of the piecewise function. So we're going to start by finding the slope of this function as we approach x is equal to 0 from the left. So to do that, we use the alternative form of the derivative as x approaches c from the left. And again, in this case, our c value is 0. So we're going to plug in 0 here, here, and here. Now, we're doing the limit as x approaches 0 of f of x. So which part of the piecewise function are we going to use? Well, we're coming in from the left. That would be x values less than 0. So we're going to use this part of the piecewise function. So we plug this in for f of x here. And then for f of 0, we're going to plug in 0 to this part of the piecewise function. And then x minus 0 is just x. Now we simplify. 0 squared plus 2 times 0 plus 1 is just going to give you 1 over here. And then we can just drop the brackets and subtract. 1 minus 1 gives you just x squared plus 2x in the numerator. Now, you could plug in 0 here, but you still get 0 over 0. So let's try to simplify this further. If I factor the numerator, I can factor out an x. So the x in the numerator and denominator cancel each other out. Now I can evaluate this limit. If I plug in 0 here, I end up getting the limits as x approaches 0 from the left is going to equal 2. Now, what does that mean? Well, again, this is the alternative form of the derivative, which is the slope of your function as x approaches 0 from the left. So the slope of this function as x approaches 0 from the left is 2. Now let's do the same thing coming in from the right. We are going to take the limit as x approaches c from the right of the alternative form of the derivative right here. We plug in our c value, which is still 0. Only this time we're coming in from the right. So we're going to use this part of the piecewise function. This is true for all x's greater than or equal to 0. So that's coming in from the right. So we take this, plug it in for f of x, and then f of 0 means we plug in 0 to this part of the piecewise function up here. Now we simplify. 0 cubed plus 3 times 0 plus 1, again, is 1. The 1's cancel each other out. out when you subtract them. And now again, you could plug in 0, but you get 0 over 0. Factor out an x in the numerator. The x's cancel each other out. And now we can evaluate this limit. We plug in 0 here for x. 0 squared is 0 plus 3 is 3. So that means that the slope of the function coming in from the left is equal to 2, but the slope of the function coming in from the right is 3. Therefore, the function has two different slopes coming in from the left and the right at x is equal to 0. Therefore, there's going to be a corner at x is equal to 0. So the function is not differentiable at x is equal to 0. Now, example 3, this says find the derivatives from the left and the right at x is equal to 8 if they exist. Is the function differentiable at x is equal to 8? So right away, you see that your function is an absolute value function. So bells and whistles and buzzers should go off in your head. You know that this is going to create a corner at x is equal to 8. So we need to prove that down here. So let's go ahead and do it. Again, we are going to find the derivative using the alternative form of the derivative, which is the limit as x approaches c from the left of f of x minus f of c all over x minus c. Why are we doing this? Because this is going to give us a number. And if we find the number, the slope of the function coming in from the left and the right are equal to each other, then we can say that the function is differentiable at x is equal to 8. But if they're not, then we can figure out why it's not differentiable. So what's our c value here? Well, again, we're finding the derivatives from the left and the right at x is equal to 8. So we're going to take 8, plug it in for c, here, here, and here. And then we simplify. F of x, we know, is the absolute value of x minus 8. F of 8 is just when we plug in 8 here for x. And then down here we have x minus 8, because that's x minus c. We then simplify. 8 minus 8 is just 0, so that cancels out. And we get the absolute value of x minus 8 over x minus 8. Now, maybe you are familiar with this type of graph. This graph looks like two horizontal lines. Coming in from the left, it's going to be a y value of -1 all the way. As you approach, x is equal to 8. And coming in from the right, it's going to be a y value of +1 all the way. But if you're not familiar with this type of graph, you can still simplify this. You can't just cancel these out. This has absolute value on it. So you need to figure out which part of the absolute value piecewise function is this. Now, if you didn't know, an absolute value function is actually a piecewise function. It is equal to x minus 8 for all x greater than or equal to 8. If I plug in any x value 8 or above, the absolute value doesn't do anything. But if I plug in any x value that is less than 8, the absolute value makes it the opposite of whatever that number is. So let's say I plug in 7. 7 minus 8 gives you -1. The absolute value of that is +1. So I need the opposite of whatever I get for that. So which part of the piecewise function is this? Well, we're coming in from the left, so that would be numbers less than 8. So that's going to be this part of the piecewise function. So instead of absolute value of x minus 8, I can write negative the quantity x minus 8. Now I can simplify. The x minus 8s cancel each other out, and I'm just left with the limit as x approaches 8 from the left of -1. The limit as x approaches anything of a number is just equal to that number. So our limit is equal to -1. Now we do the same thing coming in from the right. So again, use the alternative form of the derivative. We are again plugging in 8, except this time we're coming in from the right. So we still use our function here. And now we simplify. 8 minus 8 gives you 0, so that just cancels out. And we are again met with the absolute value of x minus 8 over x minus 8. Now you can't simplify this because this has absolute value on it. You need to figure out which part of the piecewise function, remember absolute value functions break into piecewise functions. Which part can we substitute in for this? Well, we are taking the limit as x approaches 8 from the right, so those would be x values greater than 8. So that would be this part of the piecewise function where the absolute value doesn't matter. So I'm going to take x minus 8 and I can plug that in for the absolute value of x minus 8. Now x minus 8 and x minus 8 cancel each other out and we're just left with 1. Now the limit as x approaches anything of a number is equal to that number. So what did we just find? We just figured out that this function has two different slopes, 1 and -1, as you approach x is equal to 8 from the left and the right. Therefore, this function has a corner at x is equal to 8 and is not differentiable at x is equal to 8. And you can confirm that with your graph.
You try.
Okay, doing the same thing, except we're coming in from the left and the right at x is equal to 2 this time, and seeing if the function is differentiable at x is equal to 2. So we have our function, and our variable is being raised to an exponent that is less than 1. So you think vertical tangent or cusp. Now, it's 1 over an odd number. Since it's 1 over an odd number that's greater than 1, we know there's going to be a vertical tangent here at x is equal to 2. So we need to prove that down here. So let's start by coming in from the left, and again, we're using the alternative form of the derivative so we can find the slope of the function coming in from the left. Now, to do this, our c value is again 2, so we plug that in here, here, and here. We then plug in our function. F of x is equal to x minus 2 to the 1/3 power. That goes in here. F of 2 is 2 minus 2 to the 1/3 power, and that's all over x minus 2. Now, 2 minus 2 is going to give you 0, and then 0 to the 1/3 power is just 0. So I'm left with x minus 2 to the 1/3 over x minus 2. Now, how do I simplify this? Well, technically, these are like bases. This is x minus 2 to the 1/3 over x minus 2 to the 1st. So if I wanted to simplify this, I could subtract the exponents. So x minus 2 to the 1st, I rewrite as x minus 2 to the 3/3. And if I subtract these two exponents, I get x minus 2 to the negative 2/3, or 1 over x minus 2 to the 2/3. Now, let's evaluate this. If I take 2 and plug it in here, I get 1 over 2 minus 2 to the 2/3, which is 1 over 0. Now, 1 over 0 is not an indeterminate form. That just means that your limit is going to equal infinity or negative infinity, and you just have to figure out which one it is. So we are approaching 2 from the left, which means we're approaching from x values less than 2, so like 1.9, 1.99. If I plug that in this given function right here, 1.9 minus 2 gives you negative 0.1. Now to the 2/3 power, what does this do? Well, the 2 means you square it, and then the 3 means you cube root it. So if you square it, it's going to be positive, and then if you cube root it, it's still going to be positive. So it's going to be 1 over a really, really, really tiny positive number, meaning that this limit, if you were to evaluate it, coming in from the left, is going to equal positive infinity. Now we do the exact same thing coming in from the right. So if we come in from the right this time, we again use the exact same function. We plug in the same c value, we simplify, and we get all the way to the exact same point, except this time we're coming in from the right. So if we plug in 2 again, we still get 1 over 0. But the question is, do we get positive infinity again as our slope? Well, if we plug in numbers greater than 2, that would be like 2.1, 2.01 for x here, you still get the exact same positive tiny number. So you get 1 over a really, really, really small positive number, meaning that the limit as x approaches 2 from the right is also equal to positive infinity. Therefore, because the slope of each function coming in from the left and the right is equal to positive infinity, the same infinity, there must be a vertical tangent line at x is equal to 2. Therefore, the function is not differentiable at x is equal to 2, and you can confirm that with your graph.
Spiderman, Spiderman, you turn!
Now let's do the same thing with our challenge. We have the exact same x value that we're approaching. Our c value is still 2. We just have a different function this time. Well, this doesn't look like any of the functions we talked about earlier, so let's give it a try. We're going to find the slope of the function coming in from the left. So we're going to use the alternative form of the derivative again. Again, our c value is 2, so we're going to plug in 2 here, here, and here. We then plug in what we know. We know that f of x is equal to 4 minus x squared. That goes in here. We know f of 2 is just when you plug in 2 to the function for x, and then x minus 2, boom, got that. Now let's simplify. 4 minus 2 squared is just 4 minus 4, which is 0. And the square root of 0 we know is 0. Now, let's try plugging in 2. If I plug in 2 here and here, I get 0 over 0. No, that's an indeterminate form, so I got to try to simplify this more. How can I do that? Well, let's multiply the numerator and denominator by the same radical that's in the numerator. How does that help? Well, when I multiply these two together, the radical actually disappears, and I end up getting 4 minus x squared. In the denominator, I'm not going to distribute it to each term because hopefully something will end up canceling out. Now let's try plugging in 2 again. So if I plug in 2 again, nope, still get 0 over 0. So how can I simplify this more? Well, in the numerator, can I factor out a negative 1? And if I do, don't I get a difference of squares? X squared minus 4? Yeah, so that turns into x plus 2 times x minus 2. And the x minus 2's in the numerator and denominator cancel each other out. So now I can evaluate this limit by plugging in 2 here and here, and I end up getting negative 4 over 0. So again, it's not 0 over 0, it's not an indeterminate form, it's a number over 0. So my answer is going to be either positive infinity or negative infinity. And let's figure out which one. Go back to this function right here and plug in x values that are just a little bit less than 2, like 1.9, 1.99 for x here and here. Does this become positive infinity or negative infinity? Well, this down here stays positive, but this up here would be negative. Therefore, it becomes negative infinity as x approaches 2 from the left. So let's check now from the right. So we use the same alternative form of the derivative, we're using the same function, but before we do this, look, we're plugging in x values coming in from the right of 2, so like 2.1, 2.01. Wouldn't that make this under the radical negative? And then wouldn't that not exist? Wouldn't that be an imaginary number? So right away, we could say that limit does not exist because the function is not defined for any x greater than 2. So we can't take the limit as x approaches 2 from the right. Therefore, because the limit from the left is equal to negative infinity and the limit from the right is not even defined, then we can say that the function is not differentiable at x is equal to 2. And we can confirm that with our graph. You see that this actually creates a semicircle with a radius of 2, and any x values greater than 2 are not part of the function. They're not in the domain of the function.